In the previous session, we learned about React and the tools required for React development. Today, we'll discuss different approaches to mobile application development. When companies want to build mobile applications, they generally choose between native development and hybrid development. Both approaches have their own advantages and disadvantages. Understanding these differences help developers select the most appropriate technology based on the project's requirement, budget, and timeline. By the end of the session, you will be able to differentiate between native applications and hybrid applications and identify suitable scenarios for each. A native application is designed specifically for one operating system. This means that if we want to build an Android application, we use Java or Kotlin along with Android Studio. If we want to develop an iPhone application, we use Swift or Objective C or Xcode. Since native applications are created using technologies officially supported by the operating system, they can fully utilize all device features such as the camera, GPS, fingerprint sensor, Bluetooth, NFC, and push notifications. As a result, native applications usually provide the highest level of performance and the smoothest user experience. Now that we understand what a native application is, let us see how a native application works internally by understanding its architecture. This architecture illustrates how a native application communicates with a mobile device hardware through different software layers. Each layer has a specific responsibility, and together they ensure that the application runs efficiently and provides the best possible performance. Let us begin with the first layer, which is the application layer. This is the topmost layer where the mobile application is developed. Native applications are created using platform specific programming languages. For Android devices, developers use Java or Kotlin. For iOS devices such as iPhones and iPads, developers use Swift or Objective C. Since the application is developed specifically for a single platform, it can take full advantage of all the features provided by that operating system. The user interacts directly with this layer by clicking buttons, entering text, opening menus, or performing other actions. The next layer is the native framework layer. This layer consists of the software development kits, commonly called SDKs, provided by the operating system. Android applications use the Android SDK, while iOS applications use the iOS SDK. An SDK contains ready-made libraries, tools, and application programming interfaces or APIs that developers use to access device features. For example, if the application needs to open the camera, retrieve the current GPS location, or send a notification. It does not communicate directly with the hardware. Instead, it sends a request to the appropriate SDK. The SDK acts as a bridge between the application and the operating system. Below the SDK is the operating system layer. This layer represents the Android or iOS operating system. The operating system is responsible for managing all the resources available on the mobile device. It controls memory allocation, processor usage, file management, security, multitasking, and communication with hardware devices. Whenever the SDK receives a request from the application, it forwards that request to the operating system. The operating system then decides how to execute the requested operation safely and efficiently. The final layer is the hardware layer. This layer consists of all the physical components available inside the mobile device. Example include the camera, GPS module, Bluetooth adapter, sensors, microphone, storage, fingerprint scanner, and display. These hardware components perform the actual operations requested by the application. For instance, when the user opens the camera application, the operating system activates the camera hardware. Similarly, when a navigation application requests the user's location, the GPS hardware provides the location information. Let us now understand the complete workflow shown at the bottom of the diagram. Suppose a user opens a camera application and presses the capture button. First, the user interacts with the native application. The application then sends a request to the Android SDK or iOS SDK. The SDK forwards this request to the operating system. The operating system communicates with the camera hardware and instructs it to capture the image. After the image is captured, the hardware sends the data back to the operating system. The operating system passes it to the SDK. Finally, the SDK returns the result to the application and the captured image is displayed to the user. This entire process happens within a fraction of a second. Since native applications communicate directly with the operating system through official SDKs, there are no unnecessary intermediate layers. This direct communication reduces processing time and allows application to perform tasks quickly and efficiently. As a result, native applications offer faster execution, smoother animations, better responsiveness, and improved access to device hardware compared to many other approaches. To summarize, the native application architecture consists of four major layers. The application layer, where the app is developed using platform specific programming languages. The native framework layer, which provides SDKs and APIs for accessing system features. The operating system layer, which manages device resources and controls communication. The hardware layer, which performs the actual operation using physical device components. Because of this layer architecture and direct interaction with the operating system, native applications provide excellent performance, better security, and an outstanding user experience. Native applications offer several significant advantages. They execute faster because the code is compiled specifically for the target operating system. They provide a smoother user experience with faster animations and quicker response times. Native applications can directly access hardware features such as the camera, GPS, sensors, Bluetooth, and fingerprint scanner. They also provide better security because they use the operating system's official security mechanisms. This is why applications like banking apps, gaming apps, and professional editing tools are often developed as native applications. Although native applications provide excellent performance, they also have some limitations. Developers need to create separate applications for Android and iOS. This requires different programming languages, different environments for development. As a result, development cost increase, maintenance becomes more complex, and updates need to be implemented separately for each platform. For startups or small businesses with limited budgets, this approach may not always be practical. Now, let us understand how a hybrid application works internally by studying its architecture. Unlike native applications, hybrid applications introduce additional layers that enable developers to build a single application capable of running on multiple platforms such as Android and iOS. The architecture shown on the slide consists of 5 layers. Let us discuss each layer one by one. The first and topmost layer is the application layer. This is where developers write the application code. Unlike native applications, hybrid applications are built using web technologies such as HTML, CSS, and JavaScript. These technologies are commonly used to design web pages and create interactive user interfaces. Developers write the application only once, and the same code can be reused for Android, iOS, and sometimes even web applications. This concept is called write once, run anywhere. In this layer, developers create screens such as the login page, registration page, dashboard, profile page, shopping cart, and other user interface components. The second layer is the hybrid framework layer. This is one of the most important layer in the architecture. The hybrid framework provides the runtime environment required to execute the applications. Some popular hybrid and cross-platform framework include React Native, Iconic, Apache, and Flutter. These frameworks provide ready-made UI components, navigation features, device APIs, and developmental tools. They also manage the application's execution and ensure that the same code works across multiple operating systems. Instead of writing different applications for Android and iOS, developers can maintain a single code base, making development faster and easier. The third layer is called the native bridge layer. This is the key component that differentiates hybrid applications from native applications. Since the application is written in JavaScript, the operating system cannot understand those instructions directly. Therefore, a bridge is required. The native bridge converts JavaScript functions into native API calls that the operating system can understand. For example, if the application needs to access the camera or retrieve the GPS location, the JavaScript request is first sent to the native bridge. The bridge then translates that request into native Android or iOS commands. In simple terms, the native bridge acts as a translator between the hybrid application and the operating system. Below the native bridge is the operating system layer. This layer represents the Android or iOS operating system. The operating system is responsible for managing system resources such as memory, processor usage, storage, security, networking, and multitasking. After receiving request from the native bridge, the operating system determines how to execute them using its built-in services. It also ensures that applications operate securely and efficiently without interfering with other applications running on the device. The final layer is the device hardware layer. This layer consists of all physical hardware components available on the mobile device. These include the camera, GPS receiver, Bluetooth module, sensors, microphone, fingerprint scanner, storage, display, and other hardware resources. Once the operating system receives a request, it communicates with the appropriate hardware component to perform the required task. After the hardware completes the operation, the result is returned back through the operating system, the native bridge, and finally to the application. Let us now understand the complete flow shown at the bottom of the diagram. Suppose a user opens a hybrid application and clicks a button to capture a photo. First, the user interacts with the hybrid application. The application sends the request to the hybrid framework, which manages the application's execution. The framework then forwards the request to the native bridge. The native bridge converts the JavaScript request into native Android or iOS API calls. These API calls are then sent to the operating system. The operating system activates the camera hardware and captures the image. After the image is captured, the hardware sends the result back to the operating system. The operating system passes it to the native bridge. The native bridge converts the response back into JavaScript. Finally, the hybrid framework delivers the result to the application and the captured image is displayed to the user. Although this process involves several layers, it happens almost instantly. You may now understand why hybrid applications are generally slightly slower than native applications. In native applications, requests travel directly from the application to the operating system. However, in hybrid applications, request must first pass through the hybrid framework and then the native bridge before reaching the operating system. These additional layers introduce a small amount of processing overhead. For most business applications, this difference is hardly noticeable. However, applications requiring extremely high performance, such as 3D games or advanced video editing software, are usually developed using native technologies. Hybrid applications are popular because they significantly reduce development time and cost. Developers maintain a single code base, making updates and bug fixes much simpler. This approach is especially beneficial for startups, educational projects, and businesses that need to launch applications quickly on both Android and iOS. It also reduces the effort required for testing and maintenance. Hybrid applications also have some drawbacks since there is an additional abstraction layer between the application and the operating system. Performance may not match that of native applications in graphics intensive or hardware intensive scenarios. Traditional hybrid frameworks may have limited access to certain device features unless additional plugins are used. Developers are also dependent on the framework to support new operating system features. This table summarizes the key differences between native and hybrid development. Native applications offer the best performance, complete hardware integration, and platform specific user experiences, but they require separate code bases and higher investment. Hybrid applications emphasize code reuse, faster development, and lower cost, making them attractive for many commercial projects. The choice depends on the application's requirement and available resources. Many popular applications demonstrate these approaches. Performance critical applications such as camera software, and advanced games are typically built using native technologies. On the other hand, many companies use React Native or similar cross platform frameworks for business applications where rapid development and code sharing are important. This allows organizations to deliver applications on multiple platforms while controlling development cost. Now, let us summarize. Native applications are developed specifically for one operating system, providing excellent performance and full access to device features. Hybrid applications use a shared code base to support multiple platforms, reducing development time and cost. Both approaches have strengths and limitations, and the appropriate choice depends on the project goals, budget, performance requirements, and maintenance considerations. In our next topic, we will move on to React environment setup, where we will install the required tool and create our first React application. Thank you.